families of diffeomorphisms in which we prescribe the velocity along the boundary of omega with the vector field theta, which happens to be of zero flux. And the family of diffeomorphisms that you constructed was actually nature preserving. And this was important for us in proving the isoperimetric problem, because we wanted to take a minimal set for the isoperimetric problem and move it with this diffeomorphism by preserving the volume. And of course, I said somehow I'm overdoing here because the fact is that the isoperimetric problem has nice scaling properties. So even if you don't preserve the volume, you can just scale back, and that would give you a competitor anyway. But today we will use this lemma about diffeomorphism, volume preserving diffeomorphism, I would say in a more structural way. And that's the main reason for which I wanted to present the problem in this generality. Now, today I would like to address Serrin overdetermined problem. And for this, first of all, I would like to recall a bit the motivation behind it. Yes, so, okay. Serrin overdetermined problems was motivated by two questions by Serrin's colleague Fosdick that were motivated by problem in physics and mechanics. So let me briefly recall for the benefit of students these two motivations with a little bit of details. So the first problem was about laminar flows in a pipe. So one has a possibly viscous flow, which is incompressible and stationary. So basically, Fosdick, I think, was considering the incompressible Navier-Stokes equation of a homogeneous fluid. So a fluid with velocity v and density rho, you can think rho equal to 1 for simplicity, which is subject to some exterior force, for instance, gravity that I call G, and the possible difference of pressure, which produces an acceleration of the fluid. So for me, V is the velocity of the fluid. And I'm writing somehow the second principle of dynamics for this fluid. So I'm saying that the velocity, the acceleration, that is the derivative of the velocity, which is the one on the left-hand side, is balanced by the force terms. And the force terms are the difference of pressure, the external forces, for instance, gravity, and the viscosity effect. So I'm supposing that the particles of fluid are not really free to move, but they have some kind of attachment, the one with the other. So if you have a very fast particle, it will be dragged back by the other parcels. And that is the term expressed by the Laplacian. If you think about the Laplacian, is the infinitesimal measure of the difference between the pointwise value of a function and its average nearby. Penalizing the movement, penalizing the acceleration with the Laplacian means exactly this, that you avoid particles that go too fast with respect to the particles nearby. And here on the left-hand side, basically you have the so-called material derivative of the velocity, because you take this Eulerian approach in which, rather than following each particle of the fluid, you just stay at rest and look at the velocity field at a point x at time t. Now at point x, for every different time, there will be probably a different particle of the fluid passing by. So when you think about v of x and t, x is actually x of t because it's the particle x of t passing by the point x at a given time. So when you take derivative of the velocity field, you have to use chain rule in the variable x, which is the one that produces this term here. So basically you are differentiating in the variable x, but then you have to put the velocity x dot, which produces the nonlinear term of the Navier-Stokes problem. And then of course you have the incompressibility condition, the continuity equation, that is the velocity is divergence free. Okay, then the ansatz that I think Fosdick took is that you have a horizontal pipe. So the velocity is constrained to have just a given direction. For instance, in the first, so v is a three-dimensional velocity in principle, but if a pipe is long and circular, you may, or almost circular, I mean, you may think that you have one preferred direction, for instance, the first one, and so I call u the velocity in the first direction, and I assume that the velocity in the other direction is negligible, say 0. And I'm looking for steady states of the Navier-Stokes equation, so there is no time derivative because I'm looking for equilibria in time. Okay, so if you do this and you take the divergence of v, well, the divergence of v in this case is just the first derivative of u. So you plug this information into the equation and you solve with respect to the Laplacian. Well, the Laplacian of u is the Laplacian of v1, basically, which is the only component that we really look at in this equation at this point. And so you find a nice elliptic equation because the Laplace of u is equal to the gradient of the pressure minus the external forces divided by the viscosity parameter. So if you think that the pressure gradient and the external forces and the viscosity parameters are constant, then you are basically solving the Laplacian of u to be constant in omega, for instance 1. That was the main model that Fosdick had in mind at that time. Then if you prescribe that the velocity at the boundary of the pipe is constant, well, up to the good thing about the Euler representation of the fluid is that you are in an inertial frame. I mean, I'm saying you are at rest, but mechanics is invariant if you change your inertial frame. So if you prescribe the velocity at the boundary to be constant, that is perfectly equivalent up to changing inertial frame to say that the velocity at the boundary of the domain is 0. So up to this additional change, I suppose that u is equal to 0 at the boundary. And Fosdick was also considering the very special case in which the pipe has a constant tangential stress. So the stress that you have on the pipe is somehow produced by the normal derivative of the velocity, right? Again, the acceleration is what is producing a force along the pipe. So if you want this tangential stress to be constant, you are supposing that the normal derivative of the velocity is constant on the boundary of omega. Okay, so the pipe for me is omega times r, for instance, and r is well, actually it's r times omega, okay? For the way I wrote the thing. I think it's r in the first component and omega in the others. Okay, and if you see this pink system of equations, the differential equation and the two boundary conditions were exactly the ones that Fosdick proposed to Serrin in 1971. Okay, actually, Fosdick proposed two problems which were somehow the same formulation from the mathematical point of view. And the second was related to the torsion of beams. Okay, this is a little bit more technical in a sense, so let me just briefly say what I think was the motivation. So in this case, again, you have an elastic beam, and you think that you apply some torsion. For instance, you can think that this beam is constrained on the bottom, and then you, on the top, you put a torsion on that. And you look at the displacement of the bar. So you take an horizontal section and you look how this horizontal section moves. So I'm calling here, I think, U to be the infinitesimal displacement that you obtain like that. And you start taking some ansatz. For instance, you suppose that the vertical displacement is almost the same in any plane. So the bar does not press down and up. So each layer is somehow moving horizontally. This is not really true. There is always a warping phenomena in the bars, but I mean, to keep things as simple as possible, you may imagine that this is amplification. This is amplification that reduces a vectorial problem into a scalar one. And then you look at the, yeah, for some reason it's badly displayed, so Okay, so I'm sorry, the second page doesn't display properly, but roughly speaking, I was speaking about the stress tensor, which is obtained directly from the infinitesimal displacement. And you look at the equilibrium configuration of this stress tensor that probably is not very... Yes, I don't know if you see it properly now. You should be able to see a box, which is like the infinitesimal element of the bar, with the stress tensor, which is obtained. So it's a tensor with indexes ij, which is obtained taking the derivative of the infinitesimal displacement with indexes I and j symmetrized. And you can think about the equilibrium forces, and you realize that the equilibrium configuration are the ones that satisfy this equation here, that the derivative with respect to sigma ij in, for instance, dxj sum to 0. Okay, then you just substitute the expression for the stress tensor with respect to the displacement vector, and you get a bunch of equations. But in the equilibrium formula, there are nice simplifications. So you end up discovering that there is a warping potential phi that basically, whose derivative basically reproduces this stress tensor. And the quantity that people are interested in elasticity is called the traction. And the traction is the last component of the stress tensor in the normal direction, normal to the beam. Okay. And so you plug this information into the equation, and you notice that if the exterior traction the exterior traction vanishes, this reduces the equation for the warping potential phi to a much simplified form. So you basically obtain that if there is no exterior traction, the tangential derivatives on the boundary of the warping potential are 0. But this means that the warping potential is constant along the boundary. Say again, up to normalizing, you can think that the warping potential is 0 along the boundary. And which means that the last component of the stress tensor is given by the normal derivative of phi. So the constant traction along the boundary produces an overdetermined problem for the warping potential. So again, the Laplacian of the warping potential is somehow proportional to the infinitesimal displacement of the rotation. You may think that you are rotating of some angle theta. Somehow the Laplacian of the warping potential will be proportional to that. The warping potential is going to be 0 along the boundary, and its derivative is constant. So this is just to say that the problem proposed by Fosdick, either for the straight bar subject to torsion with the traction along the surface independent on the position, so a constant traction, or a straight pipe with a viscous incompressible fluid with a constant tangential stress, boiled down to this formulation here that was studied by Serrin. Of course, all these problems have a very natural application, because of course when you want to design a pipe or a bar, you would like all the stresses produced to be constant, because it's somehow the best you can do from an engineeristic point of view to avoid unbalanced stresses, because if one part of the bar has a bigger stress than another, on the long run, the bar is going to break, or things like this. So these kind of problems have a practical importance, I would say. So the theorem of Serrin is that the only solution for this problem is to take omega to be a ball. Okay, so I would like to give a proof of Serrin's theorem, and again it will be a proof based on integral identities. So the first thing that I would like to recall is Pojar identity. So I think that basically probably all of you know the identity, but since there are students, let me give a proof of that. So Pojar identity is a general identity for semi-linear elliptic problems. So you take Laplace of u to be equal to f of u in omega, with u equal to 0 on the boundary. And you make some reasonable assumption on the nonlinearity f, for instance, that is in L infinity lock. And you take the primitive, you call big F to be the primitive of little f. And actually, the primitive that it's 0 in 0. So big F of 0 is equal to 0, and big F is the primitive of small f. Then it's very interesting, because in principle, this semi-linear equation can model basically everything. Depends what you put as nonlinearity f. The model that you consider is completely different from another model. But the beautiful thing discovered by Pojar is that all these equations, in spite of their structural difference, satisfy the same integral inequality, which is written here. So somehow there is a balance between the square of the normal derivative integrated along the boundary with respect to a weight. Now, this weight looks a little bit funny, but if you think about it's a positive weight when the boundary is convex, for instance, or it's star-shaped, so it has a natural interpretation. Well, so this boundary integral is equal to two things that up to strange constants that come out from their computation are dimensionally the same, in the sense that, for instance, if you take little f to be a power, then big F would be a power. I mean, if it, little f is a power, the power-like function with power m, big F will be a power-like function with power m plus 1. So in a sense, the term u, f of u, is, I would say, very much related to the term big F, at least for power-like functions. And now the idea of the proof is simple, though the details are somewhat tricky, but let's say that the idea of the proof is that there is a natural invariance for the Laplacian, which is scale invariance, so invariance under dilation. So if instead of a solution, you look at the dilation of a solution, you end up as a natural test function to take the radial derivatives, that is the gradient of u in the direction of x. So I call it radial derivative because I think that I'm fixing the origin and I'm taking x to be the direction in which I take the derivative. Okay, so I test the equation against the radial derivative and I integrate by parts as much as possible. Okay, sounds easy, right? Then, of course, one has to recognize some divergent structures. So here I basically wrote the equation, right? I said that the Laplacian of u is little f of u, and I tested the equation against the radial derivative. When I do that, I recognize that little f times the gradient is the gradient of big F, just by chain rule, because when I differentiate big F, I get small f, and then I have the gradient of u by the chain rule. Then here, I want to recognize a divergent structure. So I write this term, the gradient of f of u, to be the divergence of f of u x, so that when I hit the first term, I have the gradient of f of u, and then I have scalar product with x. And when I hit the second term, when I hit the vector field x, the divergence of x gives me n. Now, when I integrate by parts, when I use the divergence theorem on the divergence of f of u x, I get 0 because u on the boundary is 0. So I would get big F of 0 times something, but big F of 0 is equal to 0 because remember that big F was the primitive of small f normalized to be such that big F of 0 is equal to 0. So all this boundary term actually vanishes. Okay, so I keep this identity here, and I decide to try as much as possible to recognize a divergent structure in the first term. Okay, I want to integrate by part this. Well, I can almost do that in the sense that if I really try to add and subtract till I find a divergence, well, I find this identity. So the integrand on the left-hand side is actually equal to the divergence of something minus the divergence of something. So these are good terms because I will integrate them by parts, plus the gradient of u squared up to some constant. Okay, once I find this identity, I can actually check it by taking derivatives. But I think the way that one can find it is putting a great effort in recognizing divergent structures. Okay. Okay. Nevertheless, once you find the identity, it's an identity, you plug it in the integral, you integrate by parts, and I would say you get what you get, okay? So you use your boundary conditions, and you know that the boundary is a level set, so the normal derivative is proportional the norm of the gradient, and the normal is proportional to the gradient itself. So you use this information after you integrate by parts. You get an identity here, you compare with the first identity that you had, and this gives you the positive identity. So this looks like a trick, but with the positive identity, one can get a proof of Serrin's theorem in a sort of neat way, based on an auxiliary function, like a p function that is useful in problems like this. So the details are the following. So first of all, you want to relate the value of the normal derivatives on the boundary with the volume and the perimeter of the domain. Okay, so when the problem was formulated here in principle, we just said that the normal derivative of u was equal to a constant, say c, a constant c. But we were somehow too generous to say equal to a constant c, because the constant c is already determined by the fact that you have a solution. So it cannot be any constant. The constant is just the volume divided the perimeter. And the reason is that the Laplace of u being equal to 1 produces the volume on the left-hand side. Then you integrate by parts, you use the divergence theorem or Green's identities, and you obtain the integral on the boundary, but the normal derivative on the boundary is equal to c, so you take it out of the integral, but this determines c perfectly as the volume divided by the perimeter. Okay, so now you want to use Pojaev identity, so from this identity here, for instance, you just, okay, so the fact is that you would like to use Pojaev identity, right? So the core of these passages are here, the use of Pojaev identity. So once you use Pojaev identity, but you go backwards, going backwards is very easy, right? Because the normal derivative on the boundary was c. So if you go from here to here, you have a c square. Then you have a flux of the vector field x that you can use the divergence theorem on. So you get an integral on omega of the divergence of x, but the divergence of x is equal to n. So you end up with something of this sort. But then you have established that c is like the volume divided the perimeter. And so on the left-hand side of Pojaev, you have this strange constant here, okay? So basically here I started with Pojaev and I went backwards using that the normal derivative is constant on the boundary. Okay, then I have to look at the right-hand side of Pojaev, but in this case, since the nonlinearity is equal to 1, both the nonlinearity times the function and the primitive are equal to, up to constants, to u. So I keep track of the constant and I get the integral of u on the domain. Okay, so basically, in these two first lines, I have obtained already two interesting informations that were not obvious, at least for me, at the beginning. So in the first line, I determined the boundary normal derivative of the solution. And in the second line, I determined the mass of the solution itself. So again, the fact that the solution exists already told me two additional information about a condition on the boundary and the condition inside. And then one can look, this was somehow the original idea of Weinberger, that one can look at an auxiliary function and use the maximum principle on it. Well, if you like, this is a little bit of a Bernstein technique, if you are familiar with that. The idea of the Bernstein technique, as well as for P functions, is that the maximum principle can be used not to the solution in principle, but to any other type of quantities. And it happens that the gradient of U square has nice properties, algebraic properties, I would say, with respect to the Laplacian. For instance, if you do differential geometry, you are used to have this kind of formulas called Bochner formulas, in which you take the Laplacian of the gradient of U square. And typically, there are nice simplifications. So I would say if you have to look for an auxiliary function, the first try is the gradient of U square. Well, of course, you have to massage a bit your choice. So you put some right constant and you subtract a linear expression. And the reason for which this is a nice object to look at is that the Laplacian of this auxiliary constant is equal to the quantity that we define to be the deficit. If you remember, the deficit was like the norm square of the Hessian minus the square of the Laplacian, with the right constant normalization to make this object positive, okay? So this is just a simple computation. If you take the Laplacian of this object, you exactly recover the deficit function. And the other thing that you can see immediately is that if you compute the auxiliary function on the boundary of the domain, then U is 0 and the gradient of U square is just the normal derivative, which is equal to C. So here you get again a precise value of the P function. And you want to use maximum principle on it because remember that our deficit was non-negative. So first of all, the P function is subharmonic, and being subharmonic, the values at the boundary are an upper bound for the values inside. And actually, by strong maximum principle, either the values at the boundary are way above the values inside, so you have a strict inequality here, or the P function has to be identically equal to the value at the boundary, so the P function is constant. So of course we have this dilemma, which is which, but the fact is that the first possibility, the fact that the P is strictly less than the values at the boundary, has to be ruled out. Because if this was the case, then when you integrate in omega, you get a quantity which is strictly less than the values at the boundary n c squared over 2 times the volume of omega, okay? But then you know the expression of the P function, so you substitute the gradient of U square and U inside this object. And now you go back and you notice that the mass of U was something you knew well. Well, and the gradient of U square is related to the mass of U because you can integrate by parts, and when you do that, you get U times the Laplacian, but the Laplacian is equal to 1, so the gradient of U square is up to changes of sign and whatever is equal to the mass of U again as well. Okay, so I'm not keeping track of these constants, but just to say that there is nothing mysterious in the fact that when you integrate the Dirichlet energy for a function whose Laplacian is 1, you get again the mass of U up to some minus sign or some constants floating around. Okay, so basically here you obtain a constant times the mass of U, and the mass of U was determined in the previous slide. You put the expression that you found, And then a miracle happens. So the quantity that you get here happens to be precisely the quantity that you have on the left-hand side. But this means in particular that the first possibility that P being less to the boundary values cannot hold, because we get a contradiction from the fact that the left-hand side is equal and so not different than the right-hand side. Okay, but this means that P is necessarily constant. But then I say, wait, but P being constant means that I can compute its Laplacian. The Laplacian of P is going to be 0 because P is constant, but I knew that the Laplacian of P was equal to the deficit. So the deficit is going to be 0. Then if you remember our first lecture, we had this nice property that was saying that if the deficit is 0, then U is necessarily a ball. So with that in mind, we have completed the proof of Serrin's problem. So here I'm using my little discussion in the first lecture, in which we introduced the properties of the deficit, and we agreed that having a 0 value, so the deficit is bigger or equal than 0, but when it's equal to 0 in a region, it means that the domain is necessarily a ball. Okay, and actually you can also say that the function u is a paraboloid, if you like. Okay, so with this, I have completed the proof of, completed one proof among the many available in the literature of Serrin's problem, and I would like now to discuss the last topic of this mini course. That is a third problem related again to the elasticity theory. Okay. So this is a little bit different because it's a version of elasticity theory more related to shape optimization. Well, of course, it's just a matter of perspectives, right? Because I was also saying that Serrin's problem is a shape optimization problem after all, because you want to design a bar which is as resistant as possible, or you want to design a pipe which is as resistant as possible. And so the natural condition there was to ask that the stresses at the boundary were constant, okay, to avoid unbalanced stress at the boundary. So also Serrin type problem can be seen as an optimization, but it's not really a direct optimization problem, because it's an optimization based on physical considerations. The Saint-Venant problem has a slightly different flavor. Okay, maybe this is just philosophy, but what I want to say is that here the shape optimization of the problem is really embedded in the formulation of the problem itself. So the problem of Saint-Venant is again related with the rigidity of elastic objects, and there is this function tau that is called the torsional rigidity, which can be defined as follows. So one takes the ratio between the integral of V squared divided by the integral of the gradient of V squared, okay? So this is a little bit like the inverse of the Rayleigh quotient, but not quite, because the Rayleigh quotient would have the square inside the integral and not outside. And so in the Rayleigh quotient, when you want to look for the eigenvalues, you take the mean. So in a sense, since here we are looking at the variant of the inverse of the Rayleigh quotient, the natural thing to do is to take the max of this object. And okay, with the compactness theorems, Sobolev embedding, and so you can prove that the maximizer of this ratio actually exists. Well, if you like, it's the minimizer of the inverse ratio, which I always prefer to minimize, but it's somehow the same, right? So the maximizer of this ratio exists. And so this is a quantity that now depends only on the given domain. So you have a domain omega, you look at the maximizer of this variant of the inverse of the Rayleigh quotient. This is a quantity that depends on omega, and you call the torsional, this the torsional rigidity of the domain omega. Now the question posed by Saint-Venant is to find the domain omega that maximizes the torsional rigidity under a fixed volume. So again, you fix something, for instance, the volume of the domain, and you look for the best shape with respect to the maximization of the torsional rigidity. And so on the one hand, one can suspect that the problem is related to the sub-bubble theorem, to the isoperimetric problem, to Serrin's problem, but I would say it's not so evident at the first glance, right? Because here, to start with, we don't even have a PDE, okay? Well, but to be honest, not even in the sub-bubble theorem we had a PDE to start with. If you think about the sub-bubble theorem, sub-bubble was just taking a set with constant mean curvature. And it was a kind of magic that at some point we put it, we rephrased it in a form that was PDE friendly by looking at solutions of Laplace of U equal to 1 in the domain with U equal to 0 at the boundary. Okay, so it was a bit of a wonderful trick to be able to reduce the problem to a PDE one, so to reduce a geometric problem to the PDE one. So already for the sub-bubble problem, we had to overcome this difficulty. But I agree that for, well, also for the isoperimetric problem, we had to recast it in a convenient form, but it was clear, the isoperimetric problem was philosophically clear that it was related to the sub-bubble theorem because we proved the formula about the variation of the area, which was producing naturally the mean curvature. So for the isoperimetric problem, we were not too concerned about not having a PDE because we already had the sub-bubble theorem and the variation of the area which produced the mean curvature. So we felt we were already on business. Serrin's problem, on the other hand, was clearly addressing a PDE topic. So the Saint-Venant, in principle, looks to me the hardest because it's a geometric problem. It's speaking about a domain which I think makes our lives worse. And there is no evident PDE involved. And somehow the worst thing is that even to formulate the maximizing problem, I have to look at the function tau, which itself comes from a maximizing problem. So it really looks like an involved, like a Matryoshka problem, that we are maximizing a function obtained by maximization of a variant of an inverse of the Rayleigh quotient. It looks involved if you put it like that. Now, fortunately, even this problem can be recasted in a more convenient PDE setting. And the dilemma I would like to discuss with you, well, it's actually much more general than this, and it's called Hadamard variation formula. I will just deal with the case of the torsional rigidity here. But if you are interested in these shape optimization problems and in more general versions of the Hadamard variational formula that I'm presenting here, there is the book by Hanro, for instance, in which there are many applications of this type. So, but for the sake of simplicity, I will just consider the Sandvenant problem in this formulation. So the Hadamard variational formula is in this case this lemma here that says that suppose that omega maximizes the function tau, the torsional rigidity, then there exists a solution of the Serrin's problem. Okay, so there exists a solution u to the equation Laplace of u equal to 1 in omega, u equal to 0 on the boundary of omega, and the normal derivative constant on the omega. So if you believe in the lemma, so if you believe in Hadamard, I think that then you are done. Because if you combine the Hadamard variational formula with Serrin's theorem, you have a full classification of the Sandvenant problem, because if omega minimizes the torsional rigidity among smooth connected and bounded domains of given volume, then omega is necessarily a ball. And the proof of this is just that if omega is a minimizer of the torsional rigidity, then you have a solution of Serrin's system of equation, of systems over determined problem, and then of Serrin's over determined problem, and therefore by Serrin's theorem, you have that omega is necessarily a ball. So the only ingredient that we are missing here is Hadamard variational formula. Okay. Now, Hadamard variational formula is, or at least to me, is pretty technical. So one of the things we tried to do in this course was not to skip technical details. So this was not a mini course for the experts, it was a mini course for the students. And so we decided it was worth to put our hands in a number of unpleasant technical lemma. So remember, we did all the things that no one wants to do them, right? The Laplace-Beltrami, the construction of diffeomorphisms, the integration on tubular neighborhood, all the little technical things that sound plausible, but if you want to prove them, it's a little bit of a pain. And this is the same for the Hadamard variational formula. So we try not to skip the details and to try to give a proof of it. Okay, which goes more or less in this way. So we call J of V to be the Dirichlet energy of V. And of course, we look at this object because it appears in the definition of torsional rigidity. And again, since I prefer to minimize rather than maximize, I take U star to be the minimizer of the Dirichlet energy J among all the competitors with mass 1. So somehow I'm reverting the ratio in the definition of torsional rigidity. Then by Lagrange multipliers, I know that if U star is a minimizer, then the derivative of the energy function is proportional to the derivative of the constraint. So the constraint is linear. So when I take, well, when I mean proportional when I make the object act on some test function phi. So when I make the derivative of the Dirichlet energy act on a test function phi, I just get the L2 scalar product between the gradient of U star and the gradient of phi, okay? And when I take the derivative of the mass, since the mass is a linear object in V. When I take the derivative, I have just the integral of the test function phi. So I'm just saying that for every test function phi, the gradient of U star against the gradient of the test function is equal to lambda, the integral of phi, okay? But this means that I can integrate by parts this last term, and so put the Laplacian put the gradient, sorry, on the gradient of U star and obtain the Laplacian. And since phi is an arbitrary test function, I'm solving, if you like, in the weak sense, but it's the same because lambda is a constant. So I have a weak solution of the Laplacian of U star equal to minus lambda in omega, with U star equal to 0 on the boundary of omega, okay? The condition on the boundary was coming because I was minimizing in H10 by definition. Well, strictly speaking, I should say that this is a weak solution, but somehow by Weil's lemma, regularity theory, if I'm assuming omega to be smooth, you can take the solution U star to be as smooth as you like, if that is the thing that worries you. Then the reason for which I wanted this U star, it's because it's the one producing the torsional rigidity. So the torsional rigidity was this object here. So basically the gradient of U star square happens to be equal to lambda, just because, for instance, or well, if you normalize it, but whatever. So here I wrote the torsional rigidity, right? And now I look at this expression of the Lagrange multiplier, and if I take phi equal to U star, I get that the Dirichlet energy of U star, the integral of gradient of U star square, is actually equal to lambda, the mass of U. So one of the two masses of U on the numerator simplifies, and I just get the mass of U star divided by lambda. Okay, so I just divide the U star by lambda because I want a normalized solution of Serrin's problem, or minus lambda, better, so that I have that this U is actually solving Laplace of U equal to 1, U equal to 0 on the boundary, and the torsional rigidity equal to minus the mass of U, okay? Now I'm almost done. I'm almost done in the sense that I promised three things. I promised the Laplace of U to be equal to 1, U equal to 0 on the boundary, and then the normal derivative to be constant. Now I have three conditions. Two of them are the ones I like. The third, I find it rather useless. I would have much preferred to have the normal derivative on the boundary. So the goal now is to hammer this unpleasant condition with the torsional rigidity in order to get the boundary condition for the normal derivative. Okay. So for this, of course, I have to use the minimization property of U star, and to take advantage of the minimization property of U star, well, the minimization property of U star combined with the minimization property of the domain. So the minimization property of U star is telling me that U star realizes the torsional rigidity, but the torsional rigidity itself was minimized by my set omega, and this is the information that now I have to use. So up to now omega was fixed, and we never took advantage of the minimization property for omega. Okay, so when I said it's like a Matryoshka game, now we have to take advantage of the next Matryoshka doll. We use only the external shell. We have to put our hands inside and use the minimization property of omega. So for this, I will finally use my little lemma on the construction of measure-preserving diffeomorphisms, okay? For this, I take a zero flux theta, and because of that little lemma, if you thought that that little lemma could have been omitted because for the isoperimetric property you use scaling, that's fine. But in this case, actually, you cannot avoid. I don't think you can just play around with scaling because the Sandvenance problem is more complicated, or at least I didn't find a simple way to use scaling properties. So I use the lemma as it is. So I take a family of diffeomorphisms phi, whose velocity is given by the prescribed zero flux vector field theta, and such that the measure of omega is preserved by the diffeomorphism for everything. And then I look at somehow the counterpart of the function u. This is the same type of trick we used for the sub-bubble theorem, right? We throw on the table a useful PDE that is the one that should play a role. So we already found that u satisfies this kind of PDE in omega. Well, we look at the corresponding solution in omega t. So I call ut to be the solution of the same problem in omega t. Now, of course, one can say, well, this ut should be related to the original u mapped with the family of diffeomorphisms, okay? But, I mean, this is just at the first order because the family of diffeomorphisms is already lucky enough to preserve the volume of the set. It would be really asking too much to preserve also the differential properties of a particular type of equation. So I don't know, I don't think it's true in general, I don't believe it's true in general that ut is just the image of u under the diffeomorphism. Nevertheless, I define ut to be this type of solution, and I would like to compute the torsional rigidity of omega t using this solution. Well, this solution happens to be the minimizer of the Dirichlet energy. So exactly for this reason, right, you can go backwards and the minimizer of the Dirichlet energy is going to be unique. So whenever you can solve this equation, you actually find a representation for the torsional rigidity in terms of the solution of your torsion problem. So here I used it in one direction to start from the minimizer of the torsion problem to find the equation, but I can go vice versa and start from the equation and find the minimizer. So my solution ut is very nice because it produces the torsional rigidity for the domain omega t. And okay. And you see in the last slide, I computed that the torsional rigidity for the domain is precisely up to a sign the mass of the solution. So I know that the torsional rigidity of omega t is minus the integral of omega t of ut. And okay, now I use what I know about the diffeomorphism. So I change variable. I think that omega t is the image of omega via the family of diffeomorphisms at time t. So I have to write here the Jacobian of the change of variable. So phi is of this form. And of course, I'm neglecting higher order is in t, right? So I will be sloppy here. I put ... meaning that whatever it's here is little o of t for small t. Okay, so when I do the change of variable, yes, right, y is x plus t theta, that is the quantity that I put here. Then in principle, I should have put some little o of t, but I put it outside. And then I have to put the dy, which is 1 plus t divergence of theta. And then plus higher order terms, okay? And as I was saying, since I'm assuming omega to be regular and the diffeomorphism to be regular, basically all the quantities involved are bounded uniformly in T. So these little dots really contain higher order in T times functions that are uniformly bounded. Okay, now the first order of this expansion is 1, because it's the derivative of x, but 1 happens to be also the Laplacian of u. So I take the Laplacian of u instead of 1, and I integrate it by parts. So I separate the order 1, which is coming from here, and then I integrate by parts the Laplacian, and I get this object. And well, here I put full stop, but I should have put plus dot, dot, dot. Okay, so I'm forgetting about this dot because I'm sloppy. But there should be, of course, higher orders in the expansion. Okay, now let's compute this gradient. Okay, this gradient is a little bit unpleasant because it's a gradient of a composite function, but it's not that bad after all, because again I use the chain rule. So I take the gradient of ut, and then I have to multiply by the Jacobian of this change of coordinate. When I take the Jacobian of x, I get the identity. So the first order is just the gradient of ut computed at the change of variable. Then I have the first order coming from the Jacobian here. So I have t, the Jacobian of theta, multiplied by the gradient of ut. And then I have higher order terms. And notice that again, I'm quite sloppy because here I should have put x plus t theta, but I get rid of this higher order terms, just keeping x and putting dot, dot, dot for the reminder that I've lost here, okay? Okay, so once I have the gradient, I can compute the Laplacian. So if I take the divergence of the previous line, I have the divergence of the gradient of ut, which is 1, because I know that the Laplacian of ut is also equal to 1. And then I have to take the divergence of this product. So I use the product rule. I first put the derivative. So what I did here, well, I used the product rule in the opposite order, in the sense that I first differentiated the second term, leaving the first term still. And then in the second line, I'm differentiating the first term, taking the second term still. Okay, so this is just the product rule. So why am I doing that? Well, because I recognize 1 to be the Laplacian of something. So before I knew that 1 was the Laplacian of u to integrate by parts. Here I cannot really say that 1 is the Laplacian of this object. I have some little correction. So I look again at the function, the torsional function that I knew was equal to the up to a minus sign to the mass of u. But instead of multiplying u by 1, I write 1 as the Laplacian of this function here, minus this term to the right, to the left-hand side, minus this term that goes to the left-hand side, plus again higher order terms. Okay, so now I'm going to use this information and let's see if I find it again, this information here, okay? So I evaluated tau of omega t, I evaluated tau of omega up to the first order. So the minimality of omega tells me that when I compare tau omega t with tau of omega, this is actually a little o of t. Okay, the first derivative in 0 is equal to 0. So I substitute what I find. So I divide by t. I send t to 0. So I put dot 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 because this is the first order term which is equal to 0, and then I have here objects which are little o of 1. Okay. So the advantage of that is that I can use the previous equations here inside, and yes, and basically you see these two terms here are producing these two objects. This term has to be compared with this one, and you see that if I integrate by parts, sorry, I'm really bad in moving up and down. So if you integrate by parts, this orange term here is precisely this one here, and hopefully there is a minus sign that makes the two terms delete each other. Sorry again. So, and here I have this term here, which is this term here. Okay, so the leading order in this difference is precisely this. Okay, then now I introduce another auxiliary function. As I was saying at the beginning, right, I believe that in a sense that the solution UT is very close to the diffeomorphism of the original solution. But maybe it's not precisely so. So I define W depends on T and on X. I define this W to be the difference of these two objects. And the fact is that W is the difference between two functions that satisfy more or less the same equation, because you see the Laplace of the first term of W, the Laplace of the first term of W, the Laplace of the first term of W is written here. So there is a 1, and then there is an order of T. So 1 is exactly the Laplacian of U. So when I take the Laplacian of W, I get a big O of T, okay? And along the boundary, actually, W is a very small contribution, because in principle, U of T is not precise. So since I'm sloppy, I didn't put here precisely the diffeomorphism, right? Because if I put here the diffeomorphism, UT of the diffeomorphism would be 0, because I go back to the right domain. But that's a little error, right? Because if I want to put here the right diffeomorphism, I'm paying just a little O of T. So on the boundary, this term is 0, this term is 0, and then I only have little O of T. So the bottom line is that W is a solution of an equation that has a small Laplacian, say big O of T inside, and even little O of T on the boundary. So I use some regularity theory, for instance, Calderon-Zygmund, a global Calderon-Zygmund regularity theory, will tell me that the nabla 2p norm of W for every p, basically for every p larger than 1, is controlled by the Laplacian inside, but the Laplacian inside is order t, and some norm along the boundary, which is even more negligible than t. So the W2P norm of W is of order t, which means in particular that this WT goes to 0 when t goes to 0, in a rather strong sense, so in W2P, which means, if I go back to the definition, that UT converges to U in W2P. Well, of course, you also have this change of variable, but this change of variable is somehow very smooth, so you're not worried about this change of variable per se. Okay, so why I wanted to insist on this nice approximation result is because here I had objects which happen to involve up to 2 derivatives of ut. So I have a term which involves 0 derivative, okay. Here I have a term that involves 2 derivatives because I have the gradient, but I have also here the derivative. So this is a second order object, and this is a first order object. And now, interestingly enough, I have like a weak coupling between these objects with either nice terms given by the vector fields or linear terms in U. So basically, it would be enough to have some W to weak convergence to be able to pass to the limit. Actually, I have a strong convergence in W22. Actually, a strong convergence in W2P for all P, but I think I will use it only for P equal to 2, okay? So with this, what I mean is that I can pass this equation at the limit by the weak, or actually a strong convergence of ut to U in W to 2 omega, and obtain this nice expression in the limit, okay? So I'm almost done. Please be patient. I will do again my favorite trick, some computations to recognize the divergence structure and then use the divergence theorem. So this term here, the orange term, is has almost a divergence structure in the sense that it can be written like this, and this term integrates to 0 in omega, because when I do the divergence theorem, I get the flux of an object containing U, but U is equal to 0 on the boundary. So if I plug this information here, I can replace all this term. So this U divergence of theta stays. The orange term is this one, which is good up to this additional term that remains here, okay? Then, of course, if I have U divergence theta, I want to write it as the divergence of U times theta, but I have to pay a gradient of U times theta. So I substitute now this information here. This term integrates to 0 again, because I have U that multiplies the flux of theta on the boundary, and U is 0 on the boundary. So the bottom line is that I substitute U divergence theta with minus the gradient of U scalar product with theta. Okay. Then look at the yellow and pale green terms. Well, also these terms have a nice divergence structure because, okay, well, you would like here, if you want here to recognize a divergence structure, you have to think that the number of derivatives have to be the same. So the yellow term doesn't really match as it is because there are not enough derivatives here. There is just one derivative in u, zero derivative in theta. But here there are three derivatives, 1, 2, and 3. So if you want these two terms to have something in common, you have to invent two additional derivatives. But fortunately, there are two additional derivatives in the constant 1 because 1 is the Laplacian of u. Now this is much more balanced with respect to the number of derivatives because this object here also has three derivatives, this has three derivatives. So you may think that this is the divergence of an object with two derivatives because this also has three derivatives. And in fact, it's like that, but you have to pay a little price coming from another object with three derivatives. Okay, but then at least you took care of the yellow and the green or pale green objects, which were the ones here. So you substitute, and your identity becomes like this one. Okay. Now, this divergence part, you cannot really integrate and get rid of it because this divergence does not have u in its brackets, right? So whenever you do the flux, this is going to persist. It's not going to be zero. But there is this part still which can be massaged a bit because again you can notice that this can be written in this form. You can take the derivative outside here. So instead of differentiating theta first, you differentiate the whole product. When you do that, you have a term that differentiates theta. Then you have a term that differentiates u, which is precisely this one. But then you have an additional term that differentiates the differentiation of the gradient of u. That is this one. Okay? But this additional term is zero because when you sum over I, you are taking the Laplacian of the gradient. But the Laplacian of the gradient is the gradient of the Laplacian. But the Laplacian is equal to u, to 1. The Laplacian of u is equal to 1. So the gradient of the Laplacian of u is the gradient of 1. And this is 0. Okay? So this is a little bit of magic because you have this unpleasant term which produces a term which is still quite unpleasant, but it happens to be 0 just because you use the equation again. Then you have this term here, which has a divergence structure. And this divergence is good because it integrates to 0 because here you have a u in front. So all in all, you had millions of terms, but trying to discover divergence structure vector fields which had u in front, you got rid of basically almost all of them. And only one survived, that is this one. So you have proved that the integral over omega of the divergence of this vector field is equal to 0. Now, probably for the last time in this mini course, you apply the divergence theorem. A bit sad I cannot apply the divergence theorem again. So if I apply the divergence theorem for the last time for this mini course, I have the gradient of u dot theta. And then I have the gradient of u dot the normal. Okay, this is the flux of this vector field. But now I remember that u is 0 along the boundary of omega, which means that the gradient of u is actually the normal derivative. The normal derivative times the normal vector. So if I do that here, I get the normal derivative, and here I get the normal derivative times the normal vector. Well, in principle, I should look back at the equation and decide whether or not the gradient is going to be plus or minus the exterior derivative, right? But doesn't really matter because this identity is quadratic, so I think I can save time and say, look, even if I get the wrong sign, I get the wrong sign twice. And in any case, it's equal to 0. Anyway, what I'm saying is that the integral of the boundary of omega of the normal derivative square times theta dot nu is equal to 0. Now, if you remember when we discussed the isoperimetric problem, there was another useful lemma that we presented that was suppose that you have a continuous function that integrates to 0 against, in the flux sense, against every zero flux vector field theta, then this function is necessarily constant. Okay, this was one of the lemma, maybe it was called lemma 2 if I remember, but it's something that we presented for the isoperimetric problem. Okay, so I apply this little lemma here, and I get that the normal derivative of u, well, the normal derivative of u square, strictly speaking, is constant along the boundary, which means that the normal derivative of u is constant along a boundary. But this means that I am done because I promised to have a solution u, which was Laplace of u equal to 0 in omega, u equal to 0 on the boundary, and these two informations we already had. And then I was able to deduce from the torsional function equal to minus the mass of u that the normal derivative is also constant on the boundary. So this completes the proof of Adamar's variational formula. And so I have completed the classification of the Saint-Venant problem. So again, as a last comment, of course, you are welcome to go back to the isoperimetric problem and check that actually I could have done it in a much simpler way just by scaling. But now you realize that I wanted to make my life a little bit harder in the easier possible situation that was the isoperimetric one, in order to introduce 2 or 3 lemmata that were actually very advantageous here for the Saint-Venant's problem. So you can do the isoperimetric problem in a more straightforward way, but then you will need all these lemmata about zero flux vector fields, measure preserved diffeomorphisms, and integration against zero flux vector fields here when you discuss the Saint-Venant's problem. At least, I think, if you follow the strategy that I have outlined in the course. So I think that my time is precisely over now, and so I have to stop here. I am very happy about this event, and I hope that students also enjoyed. I apologize if the experts got bored in listening to things that are well known, but well, I hope that the students liked it at least.